Okay, so next we look at how we use limits to define integrals, particularly in the case of a function of several variables. So we sort of saw part of what we're going to need previously. So previously we saw that the value for the integral can be approximated by a double sum. So let's break down again where this comes from. So the idea is that we break up the domain into little rectangles, and each one of those has an area of delta A. Now, in this case, we're going to leave room for the possibility that each one has a different area. So we're going to use delta A sub I j. Now, on each rectangle, we're going to pick a particular x value. That's going to be xi. And then we've also got a particular y value. That's going to be yj. So these are the ways that we've partitioned up the x values with all the x1, x2, x3, and partitioned the y interval with y values, y1, y2, y3. So the area of my little rectangle is going to be delta A sub ij. The height there is going to be f of my point. So multiplying that gives you, if you think of it visually, the volume of the rectangular solid. And now we need to add up over all the possible x values, so sum over I, and over all possible y values, so the sum over j. Okay. Now, in order to turn this into a limit, I'm going to show you the the simple version and the more general complicated version. So first, what if we make some simplifying assumptions? So simplifying assumptions. Okay, so first of all, so we get this limit. Limit as m and n go to infinity, the sum as I goes from 1 to m, sum as j goes from 1 to n of f of xi yj times delta a. So what simplifying, so and that's the limit for the standard double integral over the region f of xy dA. What simplifying assumptions did we make? Well, first of all, we assumed delta A is always the same. So all my delta x is always the same length. My delta y is always the same length. So it always gives me a rectangle in my domain, delta A, of exactly the same size, first of all. Second of all, here we've also assumed, let's see, so notation, m and n are the number of subintervals for the whole interval for x and then y. And then xi is the x value on the ith subinterval, and yj is the y value on the j subinterval. And delta A, as I said, is the area of that rectangle formed by delta x and delta y. So what simplifications did we make? First of all, like I said, delta x is always the same, delta y is always the same, therefore delta A is always the same, first of all. Second of all, xi and yj, in this case, there's no special formula for them. In this case, we've always assumed that they are the endpoints on each interval. Okay. Now, what if you do not make those simplifying assumptions? The notation gets a little complicated. Let's take a look. So, in this case, written as a limit, the standard double integral is all of this. So what does this mean? So, first of all, notice that we've gone back to delta A sub ij. So here so every single rectangle in the domain, it might be a different size. So it's a sub ij, each one may be its own size. Next, on every single rectangle, we're not assuming that xi is partitioned equally. On every rectangle, the x value that you're going to use and plug in could be a different value. So therefore, the ith jth rectangle gets its own value, and we call own x value, we call it x sub ij star, and it might get its own y value, we call that y sub ij star. And then we still continue to take the sum over all x values, sum over all y values. Those are the two sums. right there. Now, what is this limit? Okay, so this is the magnitude of, well, this magnitude of delta A, that is what's called, well, so that represents the maximum value over all your delta A sub ij's. So this says that the biggest possible rectangle in my domain, I'm taking the limit as the biggest possible value goes down to 0. So if you want to be the most general and the most precise, this is the way that you have to write down these limits. Now, to actually do this calculation is a hard, very hard, difficult thing. But for our purposes, let us write down just what the limit looks like. So let's just do it in the first simple case. So this double integral, there's your function, dA equals the limit as m and n go to infinity of, we need the double sum. So the sum as I goes from 1 to m, that covers the sum over x values. The limit as j goes from 1 to n, that covers the sum over all y values. And now we need the function of xi, yj. What is that? That's just xi squared minus tan of xi times yj. And then, oh, sorry, all that times delta A. And again, this is writing down the limit using the simplifying assumptions, which is fine for our purposes.